recording now.
Thank you very much. I'd like to talk about joint work with Jesse Kass, Marc Levine, and Jake Solomon. And it generalizes the observations that there's one line through any 2 points of P2 and one conic through any 5 general points of P2. More generally, you can count degree D rational curves. The degree D rational curve in P2 is a map from P1 to P2. So in homogeneous coordinates on P1, it's an algebraic map. So we've got, it's given by U0, U1, U2 polynomials. The square brackets to denote homogeneous coordinates. And these will be degree D. UI homogeneous degree D. So a degree D polynomial has D plus 1 coefficients. That gives 3 times D plus 1. But then you've got symmetries of P1 that takes another 3 away, giving 3D, and then 1 more from homogeneous coordinates you can scale. So by a dimension count through 3D minus 1, there are about 3D minus 1 dimensions or there are 3D minus 1 dimensions of such rational curves. And so we would expect that there are finitely many degree D rational plane curves, plane for P2, through 3D minus 1 general points. We're gonna more generally than P2 look at rational curves on surfaces. So more generally than P2, let's look at rational curves on Del Pezzo surfaces. And let me remind you or explain a degree, we'll call it DSS for surface, Del Pezzo surface. For us, it's smooth. So it's a smooth projective surface with ample anticanonical bundle. And so the canonical bundle is the wedge 2 of the tangent, cotangent bundle, anticanonical bundle. So here's the canonical bundle. It's wedge 2 of the cotangent space. I'm sorry. And and the anticanonical bundle is its dual. So like minus in a Picard group. And then the degree is the self-intersection. So here's the intersection form on a surface. And if we blow up 9 minus the degree points on P2, we get 1. And then over non-algebraically closed fields, there are many more than these. And there's also P1 cross P1, cubic surfaces. And you can twist these to get interesting connected components of real points, for example. So we wanted to count degree D rational curves, and the degree is now going to be a line bundle on S. So and if you take a generic section, you get a divisor. So let D be a Cartier divisor on S, and we'll be interested in rational curves on S in curve class D. So it's a map whose push forward, it's his fundamentals class push forward is the same in Chow as this divisor, or so we've got a map P1 to S such that it's the its image is in the linear system determined by D. So we can do a dimension count as before, and with a different count. So the dimension count will give the dimension of such maps is expected to be the intersection. So we'll intersect ks in the divisor, minus ks in the divisor, minus 1. And then we expect that there are finitely many rational curves on S in curve class D through n minus 1 general points. And it doesn't matter how you pick those points. So there's an invariance of number result that says the number of such curves is independent of the generally chosen point. So it's independent of the generally chosen. So there's an open subset of choices of points such that it's invariant. So we can ask, what is this number? And there are other ways to ask this question. So these coincide with ways of counting disks. So it coincides within a sort of a symplectic context with the counts of J-holomorphic curves that coincides with Gromov-Witten genus zero invariance. And we're taking this algebraic perspective here. Here's some values. So for P2, we have this, there's one line through any 2 points. There's one conic through any 5. Another classical computation is that there are 12 degree 3 curves through rational curves through 8 points. And then for degree 4, we have 620. And for degree 5, we have 87,304. Interestingly, it sort of stopped there until there was this connection with string theory due to Kontsevich. So around 1994, these numbers were computed by a recursive formula. For Del Pezzo's under mild hypotheses, so including P1, let's do some classical values here. So if you've got 1 times the line 1 means the, say this factor times a point, and let's say line 2 means the other factor times a point. There's the Picard group of P1 plus P1. Then there's only one rational curve through 2D plus 1 points. And if you've got 2 times line 1 plus D times line 2, and ask that the curve interpolate through 2D plus 3 points, there are D times D plus 1 times 2 to the 2D plus 3. For Del Pezzos under some mild assumptions, there's a recursive formula computing all of them, in addition to low degree, more classical computation. And this is due to Kontsevich-Manin, computed all of them recursively. All right, let's switch from an algebraically closed field to the real numbers. And here we had a table giving these numbers, and we had invariance of numbers saying that there was a well-defined number independent of how we chose our points, and that fails. So the number of real rational curves can depend on the general choice of the points. For example, there can be 8, 10, or 12 degree 3 real rational curves through 8 real points. But there's beautiful work of Welschinger to give an invariant count if the curves are counted with a sign. So, he made invariance of number by counting curves together, either as a +1. So invariance of number when rational curves are counted with a sign. This sign records information about the geometry of the curve. So the particular piece of geometry in question are what happens at the nodes. So we're forcing our curve to be a map from P1. But if you had, say, degree D plane curve, so the genus, we'll call it G of a smooth curve in P2, say, smooth plane curve of degree D, this is D minus 1, choose 2. So if we're forcing it to be a map from P1, we get D minus 1, choose 2 nodes, because the arithmetic genus has to be constant in the linear system D times the line. So degree D rational curve has D minus 1, choose 2 nodes. And we can do this on a surface. So more generally, the arithmetic genus of a curve, let's call it G, and D is determined by 2G minus 2 is D times the canonical class on the surface plus D. And so it has this many nodes. So rational curve in D as D times K plus D nodes. Some in complex conjugate pairs and some that are really real. Let's look at the nodes that are really real. So node over R can look like this. We can have x1 squared plus x2 squared equals 0, or we can have x1 squared minus x2 squared equals 0. And here the tangent directions are defined over R, and so it's called a split node, and this one gets called non-split. So Welschinger says, let's call the mass of this one 0, the mass of this one 1, and ignore the complex conjugate nodes. And then if we weight our curve by the products of the masses of the nodes, we'll get invariance of number and therefore also lower bounds on the number of real curves. And so you can in particular show that there are some. So unnodal means no negative 2 curves, and we'll transfer from the symplectic setting following Ittenberg, Karlamov, and Schusten let's let S be an unnodal Del Pezzo surface over R. Let's let D be an effective Cartier divisor. And it will matter where the real points are. So there's some Del Pezzo surfaces where they're interesting connected components. Let's let n be the number of them, and we'll pick some points where little n is that dimension count from before. So let's let x1 through xn be a real configuration, meaning it's invariant under complex conjugation of n points. And we'll record how many real points are in each component. So R will be the n tuple R1, R capital N, be the number of real points on each connected component of S. Then the weighted count of the real rational curves is invariant. So then Welschinger RSD of x1 through xn, which is the count of the rational curves u through the points xi, of the weight corresponding to each curve. So the weight is going to be a product over the nodes p of u of these masses. And this actually doesn't depend on the generic choice of x1 through xn. Or general. These can also be computed. So here's some computations from Edinburgh, Karlamov, Schusten. For them, this is the Welschinger, and the Gromov-Witten are these here. although there's also a Gromov-Witten perspective on those. So here we go. There's still one real curve through any two 2 points on P2, and through the degree 2 curves through 5 points. I didn't write n here. There's still one. And then if you take r real points and 8 minus r divided by 2 complex conjugate points, you'll get a weighted count, and therefore at least r real curves through those points. Here's the degree 4. We've got 240, 144, 80, 40, 16, and 0 as we make the number of real points go down and the number of complex conjugate pairs go up. On P1 cross P1, when the degree is line 1 plus D line 2, then for any number of real points we choose, we get a weighted count of 1. And for 2 line 1 plus D line 2, we get a weighted count of D plus 1 over 2 times 2 to the D minus 1 when there's one real point, and in general when there's m. So m less than or equal to this, same parity. This is the general answer. And Jake Solomon in his thesis work gives a recursive formula for surfaces under quite general hypotheses, and showed that determined all the invariants, all of these Welschinger invariants for P2. So Jake Solomon thesis gives a recursive formula and shows this determines all the invariants for P2 in joint work with Horev. They show that it determines for the blowups. So it determines all these blowup invariants. And an undergraduate thesis student of Solomon at Princeton did it showed that the equation determined all the invariants for P1 across P1. So at least for many Del Pezzo surfaces, one can compute via recursive formula these invariants, and then they're more classical ways to do them sort of by hand. This talk is about the question that says, what about if we generalize the field? So what about over a field K? And some fields that are convenient to keep in mind, where we'll allow a finite field with Q elements and p-adic fields and Q. And we'll use the heuristic that analogous results over the reals and the complex numbers may indicate a common generalization using A1 homotopy theory. And in particular, we'll be interested in the degree. So there's a degree homomorphism from stable A1 homotopy classes of maps from this sphere. So when Pn over Pn minus 1 makes a sphere, we have a degree map that whose target contains the information of the integer count, but is often a more interesting group. So GW of K denotes the growth and defit group. So this is the group of isomorphism classes. Well, it's a group of formal differences, the group completion of isomorphism classes. Of non-degenerate, symmetric, bilinear forms. And it's useful to write down computations. And since at least stably and in characteristic not two always, bilinear forms are diagonalizable. So we've got one-dimensional generators. So generators A corresponding to the bilinear form on the one-dimensional vector space K that sends xy to axy. And if we change the basis from 1 to B, we'll change A to A times B squared. So we're reduced to only letting our generators go through the units up to squares. And this is a field presentation over a field. There are convenient algorithms for computing in this group. There's some invariance depending on the étale cohomological dimension of K. We've got the discriminant, and then the Hasse-Witt invariant, and then an Arison invariant, and the others don't have names, but you could go down, apply an invariant to some sum of generators, and eventually either prove or not prove that your generators, your sums of generators were the same. There are also lots of sort of finitely generated abelian group examples. If this is trivial, we'll get an integer and recover the integer counts listed in that first table. So, for example, the growth and defit group of C, we can take a bilinear form to its rank and get Z. And the growth and defit group of R, we've got two square classes, 1 and -1, and that gives rise to a signature. So the rank cross the signature determines an isomorphism with the Z cross C inside here, where the two have the same parity. And for a finite field, the rank and the discriminant, which is the determinant of the form when you write it as a gram matrix, gives an isomorphism to Z cross an extra Z mod 2. For the p-adics, the Witt group, which is the growth and defit group divided by the special hyperbolic form, gets two copies of the Witt group of FQ. So it's like two copies of this minus another Z. You can write that down without sweating too much. So let me actually, I want another page in here. These fit together to determine what's called an unramified sheaf. So we can extend over codimension to subsets of smooth schemes. So let's say if we take GW of E, where E ranges over finitely generated field extensions, like the rational function fields of the smooth schemes over K, these determine an unramified Misnebis sheaf. So we can take the sheafification of the group completion of the symmetric non-degenerate bilinear forms with whose values is in the OX. So GW underline, one way to describe it, and Morel shows equivalence of categories with through data like this. So sheafification of sending X to the group completion of the non-degenerate symmetric bilinear forms on a locally free sheaf on X. And it's a theorem of Oginger and Panin that when you have a section away from codimension 2, it extends over. So it's unramified in a particular sense, which includes that if you have an open whose complement is small, then you get an isomorphism. And Q can automatically extend a section here to a section over all of X. So the last notation that I'd like to introduce, or two more pieces of notation. So for a smooth scheme over K, let's consider its connected components. We had in Welschinger's theorem, we were interested in the connected components of the R points. We're also interested in connected components of C points. We just make them connected. But so we're going to be interested in connected components in this sense. So this will be a sheaf from smoother for K opposite to set. And it's the sheafification of U goes to the homotopy classes of maps from U to X, not stable. So let's get back to counting. And I didn't leave myself quite enough room here. So actually, are there questions or comments so far?
Sorry, maybe I could just ask, when you say an unramified Misnebis sheaf, is that so that's the assertion in the theorem, or
Yes, yeah, and I mean together maybe with the fact that you're determined on a dense open, so there's an injection from the values on X to the values on the generic point, and yeah, I mean yes, it's basically this is basically this assertion.
But sorry, was there a claim that once you have a definition of GW for fields, then that sort of formally determines the GW underline?
Yes, there's a procedure in chapter 2 of Morel's book for saying that yes, exactly, that there's a procedure for going from this under, you've got extra pieces of information like residue maps,
right.
that get pieced together from the residue maps on Milnor K theory, with extra bit information about eta, and yeah, there's a nice a way to go from these to this, which is a priori different, as you're pointing out.
Thanks.
Let's get back. Yes, please.
When you say unramified, some people think unramified means that GWX always injects into GW the residue of the function field. Is that what you mean?
Yes, and also that and that you extend over codimension 2.
Thank you.
Thank you. So this will be useful for counting because it can be difficult to do a geometric construction everywhere. We want to throw out codimension 2. And let's get back to the counting problem. Let's go back to counting. And we want to count rational curves. This is now from a genus 0. So this is over the algebraic closure, it's P1S. This is going to be Del Pezzo. And we want it in curve class given by D. And it's going to contain a set of points in K bar that determines a divisor over K. So they're Galois stable. And there needs to be the correct number of them. So over the algebraic closure, there's n of them. We're going to count how many of these we have and ask about invariance of number. We're going to need a list of technical assumptions that I've written here. So let's let K be a perfect field of characteristic not 2. And we're counting on Del Pezzos with effective Cartier divisor. And we've got a bunch of conditions on the degree of the surface and the degree of the curve, what Cartier divisor curve class is in. Here are some technical assumptions. We haven't introduced this yet, it'll come up later. They have to do with sort of what's written down in the literature about moduli spaces over characteristic P, in characteristic P. So what's our count going to determine? So again, U of C will have nodes. We'll have nodes, and these nodes carry a generalized mass. So over K bar, a node P of a plane curve X is a point such that the completed local ring looks like XY over the standard quadratic term, and there could be higher order, or you could get rid of them. Over K, we want that after base change, all of the preimages look like a node. So a node P is a point such that for every preimage after base change, you have a node. after some separable extension, nodes become rational. And so after and I guess we're working over a perfect field anyway, after a separable extension, and we have that the local ring looks like x squared plus a y squared. So what we're going to remember about the node, so here's the node P, and it has residue field L, and its tangent directions are defined over when you take the square root of, I guess, minus A. So this has residue field L, and these tangent directions of the branches of the node are defined over some quadratic extension. That quadratic extension is well defined. We'll define the mass of the node P to be A in the growth and decvid group of the residue field, which above was L. So K of P is the residue field. And we're going to weight curves by the product of the masses of their nodes. So the main theorem of the talk is that when we do this, we do have invariance of number. And remember, this is Jesse Kass and Marc Levine and Jake Solomon and myself. And we're going to let S be Del Pezzo, D effective Cartier divisor. K will be a perfect field. And suppose the assumptions. This includes the case of P2 and P1 cross P1 and blow-ups for those degree restrictions. We're going to then make the additional assumption that the surface is A1-connected, which again includes P2 blown up at points and P1 cross P1 and some cubic surfaces and yeah, it includes some, but not all, Del Pezzo surfaces. So then we'll let sigma be the field extensions of the points that we're going to run our rational curve through. So let this be an I tuple of field extensions. Such that over the algebraic closure, we're asking that there's endpoints that the rational curve runs through so that we get a zero-dimensional space of curves. So then there is a single weighted count that depends on the surface, the degree, and the fields of definition of the points you run through in the growth and decvid group of K, such that for any generally chosen points with these field extension, so the field of definition is given by our tuple, then our weighted count has to equal n sub s sub d sub sigma. This is the sum of rational curves U through x1, xi, and the weight has to do with the field of definition of the curve. I realized I forgot to define the transfer. So that there's a transfer on the Grothendieck-Witt group of a field here. And for a separable field extension, it's post-composition with the trace from Galois theory. So we have a transfer map LK from the Grothendieck-Witt group of L to the Grothendieck-Witt group of K, and it takes a bilinear form to the post-composition with the sum of the Galois conjugates, and it remains non-degenerate. Thanks to Galois theory. So here we're counting the number of curves we'd have over the algebraic closure, and the weight has to do with the geometry of the nodes. So it's the product over P node of U of MP. So these were in the fields of definition of the node. So strictly speaking, that doesn't make sense, but it's it does if you just multiply it out. It's the discriminant of the double point locus. So if you take the algebra of all the points that get mapped to each other, then this is the discriminant of that extension. So if you take the extension where all of the tangent vectors are defined, or if you just say that the nodes come in Galois conjugate families, that is the weight. Maybe I'll put that here. So this is the discriminant of the double points. Points of P1 mapping the same over U. Okay, so this follows from, I wanted to explicitly write down, because we had such a morass of assumptions, let's write down that an example is for S equals P2, P1 cross P1, and blowups. Let's make car K equals 0 and blow up B P2 for B fewer than equal to 5. And in more examples too. Okay, so that's the main theorem. Are there questions or comments about that?
Sorry, I was just wondering, so could you clarify what what general means, since you're working over a non-algebraically closed? Oh, sorry,
So there's an open subset of
okay.
the rational points of the associated restriction of scalars. So that if you want a collection of points like this with these, that's the same as a point on a product of restrictions of scalars, or it's an open subset of S to the n in the case that they're all K. And it's any point in there. Thank you. So this follows from actually. Okay, so I have 10 minutes left, and I'm didn't maybe manage my time perfectly. Okay, so let's remark that these numbers, they don't depend on the choice of points. They only depend on the field extension. Okay. When we don't assume that we're connected, we'll get a section of GW on the connected components. And like the R equals R1 from above, then when we have a collection of points, this weighted count will be the pullback of that section. So this follows from. But in general, the connected components are very complicated in A1 homotopy theory. So it's not easy to write down a section over that space of connected components. So let S, D, K satisfy the assumptions, but we're dropping connected component. We'll let this group of the field extensions of the points that we're interpolating our curve through to be as above, be as before. Then there is a section, we'll call it S D sigma in GW of pi naught of the restriction of scalars Li k j equals 1 to I S, such that for any generally chosen x1 through xi as above, that gives us a point of here, which gives us a point in here, which lets us pull back this. And we'll say that that pullback is what you get when you evaluate xi, and then this is equal to that same count here. For k equals r, this recovers Welschinger's theorem by taking the signature of both sides. Marc Levine showed that we had invariance just on these field extensions when the degree of the LJ, so showed when the LJK was less than or equal to 3. And we get to remove that restriction and do any degrees of points from the perspective that I hope I get the chance to say something about. And we can compute some fun examples. Let's let, so for sigma equal L1 LA, let's say that the product of all of these LJs, we're going to call it K of sigma. So here's a table. We've got S, D, sigma, and S, D, sigma, P2, well, D, line 1, D equals 1, 2, 3. It doesn't matter what sigmas we have. We get 1, 1, and then 2 times hyperbolic form, 1 plus negative 1, plus the trace form of this algebra, which we could also write as the transfer. So the classical trace forms on all of these extensions added together. So if we have P1 cross P1, and we have line 1 plus D line 2, that's just 1. But if we do 2, line 1 plus 2, line 2, we get 2, 1 plus minus 1, plus 1 plus the trace, K of sigma, Okay. And for S Del Pezzo, more generally, and D, the minus canonical class, we're going to get -1, the A1 Euler characteristic of the Del Pezzo surface itself, +1, plus this trace form. These trace forms can have interesting numbers like 5s and 10s in them, not just 1s and -1s. We'll do, say, the Fermat cubic surface. In the -ks, another way of writing that is, and if you embed in P3 1, then we get -3 plus 4, 1 plus -1 plus 1 plus this trace form, where the Euler characteristic was computed with this new result of Levine, Lahaller, and Srinivas for hypersurfaces. So remark, when the degree of the Del Pezzo, so for S with ds equals 2, 3, we can be very explicit about what the A1 Euler characteristic is. And for blowups, we can give a way to compute the A1 Euler characteristic, so that we can get a lot of fun numbers, in here from our trace forms, fun numbers in here. So those are our examples. I'd like to say a word about the proof. I also owe you an explanation of the assumptions. But I think I ran out of time. As a compromise, maybe let me tell you what that M bar was from before, although actually, I think with the amount of time I have left, it doesn't make too much sense to try to introduce M bar and rush this. So let me just leave this at that. Thank you very much.
Okay, let's thank Kirsten for a very nice talk. Are there any questions?
Kirsten, can you tell us the connection, like say over the real numbers, between these elements of the Grothendieck-Witt group, these capital N, and the number of configurations with given real and complex intersections?
So here, where did they? So this is the weighted count of real points when you go through, say, 9 real points, and then it has to be 1 complex conjugate pair to get up to the appropriate degree. And there's an 144 degree count. You get that number by applying the signature to this number with S equals P2, D equals 4 times a line, and sigma being equal to K. So there were 9 real points. So that would be sigma equal K 9 times, or R 9 times, and then C 1 time. So you'd plug in that as sigma and the P2 and the 4 times a line, and you take the signature, and that gives us the numbers that were called W above. If you take the rank, you get the numbers called N.
So
and if
for
you
each
take
of these, there's a map from the Grothendieck-Witt group to the natural numbers, which
yes,
tells
so,
you the number?
Great, yes. So every time we've got an ordering, we have a signature map. So depending on what our field is, we may have different invariants out of it. But orderings give you an extra Z, an extra way to count from the signature with respect to that ordering. And so if you do R, that natural number spits out the other one. And if you do see the rank, but any invariant of the quadratic form you could hit with the invariant with and get something that looks more classical in terms of it counting something. So you know whether you have an even or odd number of sort of weighted counts of nodes. That you can make this very explicit.
Thank you.
Thank you.
More questions? Sorry, maybe if I could ask a question. I was actually, I was wondering what sorts of ingredients go into the proofs of these counts.
Thanks. So we want to take the degree of an evaluation map. So this M bar that was above. So M bar 0n SD. This is moduli space of rational curves, stable rational curves. And marked points. And there's an evaluation map to S to the N. And we want to take a degree of this evaluation map. And the assumptions come from things that are known and are not known about, and this space is very studied. It's important to be able to orient this map. So for instance, one could orient the top and orient the bottom, but instead it's good to orient the whole map at once. And to do that, that involves understanding the ramification of this map, which has to do with how curves move around and acquire various singularities. Maybe I'll leave it at that.
And also, if I can, so is it expected that so for P2 that there would be some enriched analog of these like recursive formulas? And
I
maybe
really
also
like that. I very much hope so.
Thanks. Any further questions? Yeah, if not, let's thank Kirsten again. And